Okay, so you guys in the past have graphed quadratics. Remember vertex form and quadratic. So we're going to build on that today a little bit and then learn the absolute value function, which is actually even simpler than the quadratic function. So we have here a quadratic in vertex form. Could you tell me the vertex of this particular quadratic? 3, 2. Y'all remember that? Okay. So this is the way it works. It's y is equal to a x minus h all squared plus k. So do you remember that? And then the vertex is always going to be at h comma k. So that's kind of like your most important point. Is this coming back? Well done. Okay, so let's sketch it. So 3, 2. So there's the vertex. This is going to open up because it's a positive 1 out front. And in this unit, you're going to have to graph these. You're going to have to know what I call the moves for these. Your teacher may or may not have taught you this in 9th grade. It is what you learned in 9th grade, but we're not going to actually do data tables for these. We're going to use moves. In other words, with a quadratic, you go 1 to the right, 1 up. 2 to the right would be what? 4 up. Do you remember that at all?
No.
Okay, 1 to the left, 1 up. 2 to the left would be 4 up, and it's symmetrical across the axis of symmetry. So it looks something like this. Is that in any way ringing a bell with you?
Yeah.
Okay.
What is it again?
So I'll do a data table once just to show you. Okay. So -2, -1, 0, 1, and 2. This is probably how you did it when you learned it in 9th grade. We're going to be doing these more quickly than you did in 9th grade. So it's the function, it's the square function or the quadratic function. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So it creates symmetry about the, well in this case, this is like your parent function. It would create symmetry across the y-axis. This has been shifted 3 to the right and 2 up, but it hasn't been stretched or compressed. So it's going to have these same exact moves. So when I say 2 to the left, 4 up, I'm really just plotting that data point from the transformed or translated origin. Okay, so that's where my vertex has been moved. So 2 to the left, 4 up, 1 to the left, 1 up, 1 to the right, 1 up, 2 to the right, 4 up. So does that make sense to you? Sort of. We're going to do that a lot, so I'll keep doing that. Okay, tell me the vertex on this one.
1,
And you have to change the sign of this because of the x minus h here. So it's -1, -1, so put that in place. Now, this one has been transformed. It's actually been stretched by a factor of 2. So rather than plugging in an x into that every single time and getting a value out, I'm just going to stretch the function. I'm going to change my moves. So when I go 2 to the left, I'm no longer going to go up 4. I'm going to go up twice as much. I'm going to go up 8. So, and I'm not even really all that concerned about that point, but I would go 2 to the left, and I would go up 8, which would put me at 7. So it'd be right here-ish, I think. Okay? All right, and then 1 to the left would normally go up 1, but now I'm going to go up 2. So it's stretching by a factor of 2. So I still use my same x values. Like I still use those as my moves left and right, but then I stretch for the y movement. So let's do the same thing on the right side. 1 over would normally be 1 up, but I've got to stretch it. I go up twice as much. 2 over, I'm going to have symmetry, so I can just go up and put it at the same level. And that's the sketch for that one. Okay. So this one right here, what's the vertex? -2 and 3. And then it reflects it downward. So when I do my y moves, I'm not going to go, I'll go 1 to the right, but I won't go 1 up, I'll go 1 down to make that reflection happen. So I'll show you how that works. So -2, 3 will be right here. 1 to the right is now going to go down 1. 1 to the left will go down 1. 2 to the left will go down 4. 2 to the, I said 2 to the left. 2 to the right will go down 4. 2 to the left will also go down 4, though. And it would be right there, I believe. And then there's your quadratic. Without doing any data tables, this is what you're going to have to do this unit, okay? So I can tell a lot of y'all have never done that. I can tell. That's fine. We'll work on it. Now, let's look at the absolute value function. First of all, what is the absolute value function? Like, do you know what absolute value is?
The highest point.
The absolute value, remember the symbol that looks like, well, let's just do these, and then this might help you. The absolute value of 5 is 5. The absolute value of negative 8 is what? 8. It is really just a distance. It's a distance from 0 on the number line. Okay. And then we're going to actually solve these. So if I have this, an equation like this, what would the absolute value of x be that would give me 3? What could x possibly be? Could be 3 or a negative 3. So this is going to have like a split, just like the quadratic has, but this one's going to be in a V shape. Okay, so let me kind of show you what that looks like. So this is just our parent function. So when I say parent function, I mean you're going back to the basics. You don't have any translations at all. No left-right shifts, no up-down shifts, no stretching, no compression, no reflection. Those are all the things we're going to review. So, yes.
I thought there was one like the opposite. Is that just for the negative?
Well, yes, that's just for the negative. So if I did this or I did this, do you agree both of those would give me a positive 3? So I'm saying here, x is either 3 or it could possibly be a negative 3. So that's kind of like a solution. So we're going to have 2 solutions for every distance, okay? Now, so I'm going to sketch it for you. It's simply this. I'm going to do a data table this one time, and you'll know the moves. So negative 2, negative 1, 0, 1, and 2. What's the absolute value of negative 2? 2. What's the, and this is what I'm doing here, guys. What's the absolute value of negative 1? 1. What's the absolute value of 0? 0. 1 and 2. So are y'all okay with that? So it's similar to the quadratic in that all the signs turn positive in the parent function. What's different, though, is just basically forming a line. It's going to form a line. So let's put those points in place. So do you see this is really just a line with the slope of 1? This is a line with the slope of negative 1. So make sure you know that they have opposite slopes. That's not what I want to do. Okay? And do your best to make it straight. Now, we're going to do everything with this function just like we did with our polynomial unit. So domain, range, increase, decrease, and all that good stuff. So what do you think the domain of this is going to be? Very good. What's the range? What's my lowest possible y? 0. So my lowest y is 0, but it can go up to infinity. Remember to use brackets here. The vertex here is at 0, 0. There is a minimum at 0, 0. Now, intervals of increase and decrease. It decreases and it increases. But guys, this is what y'all really struggle with a lot on the little quiz yesterday. This is the interval that I want to write about. These values. So it's negative infinity up to 0. These are all my decreasing, so I'll put decreasing here. And then it increases. I'll do increasing in blue. So here's increasing. But it's these x's that I'm writing down in the interval notation. That's what y'all miss. A lot of y'all miss that. Some of you got it, though. So it's just, we just got to keep working on it.
We can put this back after everyone does it.
Yeah. Yeah. I really would like to, I want to give it back as soon as possible because we're building on those same concepts. So do y'all agree that this would be negative infinity to this x of 0? That would be a decrease. So negative infinity to 0. And then 0 to infinity is where it increases. The x-intercept can be read from the graph. This time, it won't always be, but it's 0, 0. The y-intercept happens to be the same thing. In behavior, is this an even function? Does it have symmetry across the y-axis?
Yes.
It is an even function. This is not a polynomial, though, is it? So you can't use just looking at your exponents to do this. You have to know, you have to see the graph, and then you have to evaluate it. But it would be even. So the end behavior is going to be as x goes to both positive and negative infinity, y goes to positive infinity, because it's an even function. Okay? So we've already talked about even. Let's go ahead and circle that. So where is the graph above 0? So I'm going to basically take this off because now we're changing the scenario. Now I'm wanting to know where is it positive? And this is above. So isn't it everything?
Yeah.
It
No.
almost. It is not positive right there. It's neutral right there. So I cannot use 0 as part of that solution. So it's going to be from negative infinity to 0, not including 0, in union with 0 to infinity. It is never below, though. Never. Now, if I change one simple thing, if I had changed this to have an underline right there, how would that change my answer? So I'm going to do that off to the side just so make sure you understand that. If I changed it to that, it would be every single x gives me a positive or a 0 y. Does that make sense? Then I could include that. I'd go back and bubble that in and include it in my solution. All right, so let's do one where we have some transformations. So flip over to the back. We have a lot to do here. I'm going to go pretty fast through this. Okay, the first thing I do always is the vertex. What is the vertex here? 2 what? 2, comma 0. Very good. I'm going to get this a little bit smaller if I can. That might help a little bit. Okay, I just want it all on the screen at one time. Okay, so 2, comma 0. That's really important to go ahead and write that down because that gets you started. So essentially, it's just moving 2 to the right. So it's a translation 2 to the right. No stretching or compression, so I'm just going to use my normal moves, which is just a line up to the right with a slope of 1, and then to the left up with a slope of 1 as well. Okay, and do these points as precise as you can because that's going to help you find like your x-intercepts, y-intercepts. I hope I did that precisely enough. Okay, that's not great, but you get the gist. Okay, so domain is everything. Range is still 0 to infinity because it didn't move up or down, so it's just 0 to infinity. It is a minimum still. Now, our intervals of increase and decrease have changed because it shifted. So let me do I'm going to do a little dash line here, right here, to show you. This is where it changes behavior. You can't really see that, can you? So it's going to decrease until you get to this x of 2, and then it increases from there. So it's going to have an interval of increase from 2 to infinity and decrease from negative infinity up to that 2. So it's that x of that vertex is where it changes the direction. X-intercept is what? 2, comma 0. The y-intercept, if I did it right, should be 0, 2. Okay, so you went up 1 over 1, up 1 over 1. So 0, 2. End behavior is as x goes to plus and minus infinity, y goes to infinity. Now, where is it positive? This is the same thing. It's going to be from negative infinity. Well, it changes. It takes a break at that 2. So at the 2, it's not positive, it's just a 0. So union with 2 to infinity. Okay, where is it less than? Never. Is this an even odd or neither? It's neither because it got shifted to the right. So it's a neither. Okay? Now, I want you to try H on your own, and then we'll check in and look at that in just a second.